Okay, the first thing that Griffiths talks about in his book is the wave function. So this is where we will start as well. Okay, just a random thought that occurred to me this morning about preparing lectures and lessons on YouTube is that, one of the advantages of YouTube is that you can get a taste of what you're about to learn without having to go through college applications, actually attending college, selecting a major, etc. So you can just watch a YouTube video. Not necessarily from me, I'm not claiming to be an expert or an authority on the matter, but I did teach before, and I was also a student once. And what I'm trying to say is that, you back in the day, you used to just go into the unknown, if you know what I mean. Whereas now with YouTube, you can just watch a lecture on quantum mechanics, on stochastic calculus, on group theory, on cryptography, whatever it is, you name it, and get a feeling of whether you actually like something or not, and whether you want to get into something or not when you are really young. Maybe in high school even, you can watch these videos and get ahead. This is what I'm trying to say, okay? So I hope these videos are useful. The only negative aspect of preparing these videos that I experience is that I really like actually being in a classroom or in an auditorium, etc., in a lecture hall, and actually interacting with my students. This is something you don't get on YouTube, but I don't know, if I become famous, maybe I will get the chance to actually teach this in a classroom again, or maybe get a job and film the lectures as we go, etc. So anyway, this was totally irrelevant to the class, so let's get into the matter. So in this chapter, we will just talk about the wave function, okay? So we will discuss what the wave function expresses. We will actually use the wave function without deriving it, okay? So the derivation of a wave function stems from the solution of the Schrödinger equation, which we will study in the second chapter, okay? So in this chapter, we'll just talking and using wave functions to derive stuff, okay? So the first thing I want to mention is that in general, throughout the course, I mean this set of lectures at least, okay? And again, I have to eternally apologize for my horrible, really horrible handwriting. But I don't know, I guess I think faster than I can write, something like that, and this creates a problem. So I don't know. So in general, throughout the course, we will focus on non-relativistic quantum mechanics, of a single particle. Or a few particles. Because at some point we will talk about spin and coupling and stuff like that. So what do I mean by single particle? So one electron orbiting a proton, for example, which is also known as the hydrogen atom, or one electron orbiting outside the first closed shell of the lithium atom, okay? So you can think about that electron as being independent of all the others and derive stuff if you want. Or a proton inside a nucleus. So focusing only on that makes it a single particle, okay? So that's what a single particle means. And okay, since we will be starting really simple, one particle in one dimension trapped in a potential and doing stuff. So what do I mean by potential, we will see later. And actually, okay, let me show you. A potential might be the harmonic oscillator potential. potential that looks like this, okay? And inside this potential, we will see that the particle can do certain stuff, okay? So that's your particle, that's one dimension, that's your potential, and the particle can do stuff. What do we mean by non-relativistic? So in general, the rest energy of particles is given by the most, probably the most famous equation in physics, which is m naught c squared, where m naught is the rest mass, and this is actually the rest energy, okay? So if we take the example of an electron has a mass of 9.11 actually, times 10 to the negative 31, times 3 times 10 to the 8 squared. And give me a second, because now I'm kind of improvising. I didn't plan on talking about this, but I want to stress it. So 9.11 times 10 to the negative 31. I'm using my calculator now behind the scenes. This gives you 8.2 times 10 to the minus 14 joules. And as it's customary in quantum physics, you don't use joules, you use electron volts, okay? And I hope you guys know what an electron volt is, but the definition is that 1 electron volt is 1.6 times 10 to the negative 19 joules, okay? So the rest energy of an electron is, let me do the division. I actually know the result, but I just, okay, 511 point, actually 512 is what my calculator gives me. So, oops. So 512.4 kilo electron volts, okay? Or usually it's written as 0.512 MeVs. Okay, so non-relativistic means that the electron has kinetic energies, or in general total energies, much lower than that, okay? Because if you start having electrons moving with more energy than the rest mass, then you can start having a pair creation phenomena, okay? Or you can have, in general, you have enough energy to produce other particles, okay? So then the whole Schrödinger equation business does not work. You need field theory, and quantum field theory is a totally different, it's not a totally different, I mean, it's another field of physics that studies particle interactions and things moving at really, really high speeds with really, really high energies. And the appropriate treatment is different than the treatment that the Schrödinger equation gives you, okay? So this is what I mean by non-relativistic. And let me get into the point that I actually wanted to talk about when I started, when I made these notes that I'm following along as I prepare this, as I'm making this video. So I like to do this when I teach, in the beginning of the lessons at least. So let's talk about physics in general. So we have large objects, okay? So also called macroscopic. And macroscopic objects can be anything that is kind of visible, but it's not necessary to be visible. So macroscopic objects are objects that obey Newton's laws, usually, okay? So bacteria, even though they are tiny, they are macroscopic objects because they consist of billions and billions and billions of atoms. So it's a macroscopic object, okay? So that's something that quantum mechanics cannot study at the moment, okay? So, and probably not in the foreseeable future, okay? So, yeah. So large objects are macroscopic objects, and if they move with low speed, actually let me make some space because I will run out of space. I have a small screen. Oops, sorry. Wrong tool. Which is the tool that allows, okay, this is the tool I was looking for. Okay, so let me move this there so I have space. All right, and how do I go back? Okay, so okay, so low speed, which means V much slower than the speed of light, and high speed, which means v close to the speed of light. Nothing can move faster than light. Okay, so if you have large objects and you want to study their motion, and if they move with low speed, you use classical mechanics. Okay, which means Newton's laws of motion, or you can use Lagrange's or Hamiltonian's approach to classical mechanics, etc. So that's what you use. If these objects are macroscopic and they nevertheless move with the speed of close to the speed of light, you need to use special relativity. Okay. And yes, the one developed by our friend, Professor actually, Albert Einstein. Okay, so let's say we have small objects. What do we mean by small? Okay, okay, and let me write in parentheses microscopic. Okay, we mean atoms, electrons, protons, neutrons, and so on. Okay, so how small are these objects compared to everyday experience? If I remember correctly, nucleus is about 1 billion times smaller than our hair. Okay, so it's that much smaller. Okay, so this is what I mean by small. Okay, if these small objects move with low speeds, we use quantum mechanics to describe them. If they move with high speeds, I already gave it away when I made this silly analysis here with the electron having a rest mass. Actually, okay, let me draw this line here. Okay, so if an electron moves has an energy of about 1 MeV, you cannot use quantum mechanics anymore. You need to use what is called quantum field theory. Okay, so quantum field theory studies particle interactions, pair creation, pair annihilation, processes like that, processes in which particles disappear or get created because you're dealing with really high energies. Okay, whereas quantum mechanics deals with low speed objects. So with quantum mechanics, you can study atoms, like how the electrons distribute themselves around an atom. Quantum chemists use quantum mechanics. Nuclear theorists, like myself, use quantum mechanics because the nucleus is non-relativistic. Like if you want to study its structure, because, okay, I mean, in high speeds, it becomes relativistic and then you need QFT. And so on. So quantum mechanics is useful for quantum chemistry, solid state physics, people who study materials, quantum chemistry, I think we already said that, nuclear physics, and I'm sure I'm forgetting things, but yeah, something like that. So small objects, low speeds, we use quantum mechanics. Okay, let's continue. So let's mention one more thing before we dive into quantum mechanics. Let's talk about Newtonian mechanics for a moment. So Newtonian mechanics. So in Newtonian mechanics, I'm sorry. The holy grail, I guess, the most important thing is to find, in Newtonian mechanics, we want to find x of t, and I am assuming here that we are dealing with one-dimensional problems, okay? So x of t is the trajectory, okay? So in Newtonian mechanics, we want to find x of t, the trajectory of an object under the influence influence of some force. And that force usually has the form f of x of t. So it's a function of both position and time. So here's your particle, which is again macroscopic. Okay, so it's an object. Okay, maybe it's a ball or something like that. So let's say there is a force f of x of t acting on it. What's gonna happen? It's gonna make it move, okay, to a new position. Okay, the force will still be there, so the particle will, or the object will cover some distance. And if we know x of t, we can tell the position of the object at any future time. Okay, so how do you find x of t? The recipe is the Newton's second law. Okay, so which tell us that the sum of all forces is equal to mass times the acceleration, and these are vectors. Okay, it's a vector equation because both acceleration and force have a direction. Okay, so assuming f is m d squared x over dt squared, actually sorry, assuming that sigma f is just f is the magnitude of the force, then f is just m d squared x over dt squared. Okay, and for conservative systems, so these are systems in which energy is not lost, energy is just converted between kinetic energy and potential energy ad infinitum. Okay, so no energy is lost, no friction, no air resistance, forces like that. So for example, gravity is a conservative field. Okay, so for conservative systems, okay, the force is the gradient of x, or the partial derivative with respect to x. Okay, so you can use 1 and 2 to write m d squared x over dt squared equals to the partial with respect to x. And if you solve this equation, you get x of t. Okay, so for example, an example of a conservative potential is, oops, typo. For example, v is 1/2 kx squared. If v, sorry, this is the potential of a harmonic oscillator, the potential for harmonic oscillator motion. So this stems from, if you have a force, a restoring force minus kx, and if you write this as minus theta v over minus partial v over partial x equals to minus kx, you find that v is 1/2 kx squared. Okay, so for this potential, okay, we can write let me think, okay, m d squared x over dt squared is equal to minus kx, which is the partial with respect to x of this potential. So we can write this as d squared x over dt squared plus omega squared x equal to 0, where omega squared is k over m. Okay, and this is the most popular equation in physics. Some say this is the only equation that physicists were able to solve. So this is the differential equation for harmonic oscillator motion, and the solution is well known and is given by x of t equals to a cos omega t plus b sine omega t. Okay, so two solutions because it's a second order ordinary linear differential equation. Okay, and is there anything else I want to mention here? Oh, one thing that comes again and again in physics is that if you have physical variables like omega t, for example, inside functions such as cos, sine, e, exponential functions, tangents, whatever, usually omega t is a dimensionless quantity, okay? So, usually so what I'm trying to say is that in physics, if you have cos x times y times z, or tangent of x over y, or things like that, the variables in parentheses usually are dimensionless, okay? So usually we use square brackets when we are dealing with dimensions or units used to express a physical quantity. So this is omega times t. What are the units for omega? Radians per second. Radians are dimensionless, okay? So for omega, we use seconds to the minus 1 times seconds, and we get 1, okay? So omega t is indeed dimensionless. Okay, and by finding x of t, you are not totally done. You actually need to find a and b, these constants here. And to find these constants, you usually need to be given initial conditions, okay? So for a complete solution, for x of t, you need two initial conditions which are usually x, the position at time 0, and the velocity at time 0, which is dx over dt at time 0. Okay, actually, let me write it at t equal to 0. Okay, so with these two conditions given, you will be able to find a and b. And once you know x of t in Newtonian mechanics, you can derive all other dynamic variables. And in physics, when we use the word dynamic, we mean something that involves motion, okay? So we can derive all other dynamic variables of interest, such as v of t, a of t. So remember, the velocity is dx over dt, the acceleration is d squared x over dt squared. You can calculate the momentum, which is mv. You can calculate the kinetic energy, which is p squared over 2m, and you get the idea, okay? So all you need to do is to find x of t, and that's it. You're done. I mean, you can find anything you want to know about the system by finding x of t. So by solving that equation known as Newton's second law, which leads to a differential equation that can be solved if you know the force or the potential. Okay, I don't want to mention more about this because we are still talking about Newtonian mechanics. So now it's time to talk about quantum mechanics. So in QM, I will be writing it as QM for to save time. So in quantum mechanics, we don't search for x of t, but for the wave function psi, and because I'm actually Greek, actually in Greek that's psi, but okay, people call it psi or psi, I will be calling it like that. So for the wave function, in quantum mechanics, we search for the wave function psi x of t. So Psi is actually a function of both the position and time, okay? And this wave function satisfies, so we are searching for the wave function satisfying the infamous Schrödinger equation. Schrödinger was an Austrian physicist who derived this in the 1930s, something like that. Or maybe 1920s. Maybe it was 1926, 27, something like that. This is not a history of physics class, so you can just learn about Mr. Schrödinger on your own if you want. So, and he won a Nobel Prize for that. So we need to find, so in quantum mechanics, we need to find this equation, this wave function that satisfies this equation. I times h bar times the partial with respect to t equals to minus h squared over 2m, and then the second partial with respect to position of the wave function plus the potential times the wave function, okay? And I will call this equation 1 because we will be coming back to this again and again. H bar is defined as h over 2 pi, and it's equal to 1.05 4573 times 10 to the negative 34 joules times seconds. So given initial conditions, psi since the Schrödinger equation is actually a partial differential equation because we use this symbol, okay? And let me explain actually what the partial differential equation is, what the partial derivative is actually to those who are not familiar with partial derivatives. Let's say we have the function f of x, y equals to x squared plus y, something like that. Then the partial with respect to x is simply 2x. So when we take the partial with respect to x, we only take the first derivative with respect to x, and we treat y as a constant, okay? So the derivative of y with respect to x is 0 if y is constant. And then the partial derivative with respect to y is 1, right? Because x squared is a constant as far as the partial differentiation with respect to y goes, okay? Right. So because the Schrödinger equation is first order with respect to time, okay? It's a first order differential equation, partial differential equation with respect to time. We only need to know psi of x at t equals 0. So we only need to know one initial condition. One initial condition. Okay, to fully find, actually it's better, okay, to fully find psi x of t at all times. Okay, so this is different already from the Newton's equation, in which, because the Newton's differential equation is second order with respect to time, you need two initial conditions with respect to time, whereas with the Schrödinger equation you just need one, okay? And we will come back to this again and again as we go through this course. And what else do I want to mention at this point? So this is the infamous Schrödinger equation. You need one initial condition to find psi of x of t at all times, given that you already found psi of x of t, okay, by solving the differential equation for some potential, okay. And let's say that psi x of t is the holy grail of quantum mechanics, of QM. Okay, just like x of t is the holy grail for Newtonian mechanics, classical mechanics, okay? Even with Lagrangian mechanics, your goal is still to find an equation for the trajectory of an object, okay? And again, I remind you that Lagrangian mechanics is equivalent to Newton's equations, okay? But Lagrangian mechanics is better to use when you deal with complicated coordinates and such. But anyway, let's not digress again. So this is all I wanted to say about the Schrödinger equation and the wave function for now. And let's start talking about what kind of information psi x of t gives us, okay? So let's talk about what is called the statistical interpretation of the wave function. So the title of the next topic is what kind of information does psi x of t give you? Okay, and this is known as the statistical interpretation of the wave function. Okay, so let's start by saying something that now digresses completely from Newtonian mechanics. So the absolute value of the square of the wave function actually expresses the probability of finding the particle at position x at time t. Okay, and more generally, this quantity here, psi x of t squared dx, is equal to the probability of finding the particle between x and x plus dx. Okay, so let's make a plot to better understand what I'm saying. So if you plot psi squared with respect to x, and if your plot looks something like this, for example, okay, let's see, actually, let me make it, okay, something like this, okay, so, oops, no, this is not what I want, I'm sorry, I keep changing my mind. So k goes to 0, something like this, okay. Let's say that this is your wave function, okay? Then the most probable position to find the particle is, can you guess? Right there, okay? So this position, let's call it A, that's the most probable position. Why? Because psi squared is maximum, okay? And can you guess where the least probable position is? Over here. So B, let's call this position B. This is the least probable position, okay? And what do we mean by this expression? So we said that this expression is the probability of finding the particle between x and x plus dx. So let's say that this is some position x, and this is the position x plus dx. Therefore, this interval is just dx. Actually, let me get it out of there because I will need to do something. So this width over here is dx, okay? Then the area under the curve, so this thing over here, is the probability of finding the particle between x and x plus dx. So the integral from x and x plus dx of psi squared dx gives you this area over there, okay? So this is what the wave function expresses, okay? It expresses probabilities, not necessarily trajectories, not trajectories at all, actually, okay? It expresses the probability of finding the particle somewhere in space and at some particular time, t, okay? So let's see, let's see an example. So, oops. Let's work through an example. And again, in this introductory chapter, we will not be deriving the wave function. We will be using wave functions to show their properties, pretty much, okay? So for a particle trapped in the 1D harmonic oscillator potential, let's call it HO, given by 1/2 kx squared. Similarly to the example we saw with Newton's differential equation, okay? And we also write 1/2 kx squared as 1/2 m omega squared x squared, okay? So for this example, the solution is psi x of t equals psi naught of x times e to the minus I e naught t over h bar. Okay, where e naught is 1/2 h bar omega. I hope you're still all there because things started getting scary, I guess. Okay, but okay, for this potential, if we take this potential, we will actually do this later in the course. So if we take this potential, plug it into this equation, okay, the Schrödinger equation. So we will plug it here, actually, okay? If we plug it in there and solve this equation, we will get this solution and many others, as we will see, okay? So, but this is called the ground state solution, okay? It's one of the solutions, and then there are infinite many other solutions that have certain properties we will talk about later. But for the ground state, we use this index 0 to track the ground state, the first excited state, etc. Okay. So for the ground state, this is the wave function, the full wave function, okay, that includes time. And let me show you one more thing. Remember when I said that when you see functions that have physical quantities as arguments, then the quantity in parentheses is dimensionless. Remember that? So I'm talking about this expression over here, E naught T over H bar. Okay, what are the dimensions of this? Energy has dimensions of joules, time has dimensions of seconds, and H bar has dimensions of joules times seconds. So this is a dimensionless quantity. Okay, remember we said that. Psi naught of x, so the position space wave function is given by m omega over pi h bar to the 1/4 times e, and I'm writing it as exponent of minus m omega x squared over 2h bar. Okay? Therefore, remember when I said that usually we deal with the probability density function, as we say, which is found by forming this quantity here, which is nothing but this, xt times psi x of t. So the complex conjugate of this is e to the I e naught t over h. So these factors cancel, and you're left with c naught squared of x, which is just m omega over pi h bar to the 1/2 e to the minus m omega squared x squared over h bar. Sorry, it's not omega squared, it's just omega, I'm sorry. So, okay, let me rewrite that, m omega. Okay, let's do a dimensional analysis again for this factor over here. Let's go see whether it's actually dimensionless, as I promised. So m omega squared x over h bar is the argument in that exponent. So we have kilograms for the mass, seconds to the -1. Why did I write omega squared again? I don't know. Okay, position has dimensions of meter squared, and then h bar has dimensions of joules, which is kilograms, joules times seconds, I'm sorry, kilograms meters squared over seconds squared. So all these seconds cancel, this cancels, this cancels, and wait, something's wrong. No, it's correct, sorry. Kilograms seconds to the -1 meter squared, kilograms meter squared second. Okay, that's correct. Yeah, they actually cancel. So we get 1. Okay. Now let's go find the dimensions of this quantity. Okay. So what kind of dimensions does that quantity have? So m omega over pi h bar to the 1/2. This quantity has dimensions of kilograms, seconds to the -1, and then joules times seconds to the 1/2. So this has units of kilograms, seconds to the -1, and then let's expand the joules into kilograms, meter squared, second squared over, and then you still have the seconds. So seconds cancel, kilograms cancel. The whole thing is to the 1/2. So that factor has quantities of meters to the -1. Okay, that's an interesting quantity. Why does it has units of meters to the -1? Because recall that the probability of finding the particle between x and x plus dx is this quantity here, psi squared dx, which has units of meters to the -1 from the wave function, and then the dx has units of meters, so the dimensions is 1. Okay, so and as it should, right? Because this is a probability, and probabilities are dimensionless. Okay. Let's go see. I hope I didn't lose you yet. We are still just talking about wave functions and what they represent. So, as I claimed in the beginning, wave functions express probabilities of finding the particle at the position x and time t. And if you want to find the probability for a range of positions, then you have to do the integral, okay? And we use this example of the harmonic oscillator potential ground state to demonstrate certain properties of wave functions. Okay. Okay, let's move on. Let's plot psi naught squared. Okay, so psi naught squared with respect to x is just a Gaussian that looks like this. Okay, so the most probable position is the origin, actually, right? Most probable. What else do I want to say? Gaussians have the property that no, let's keep it here. No. Okay, I will stop this video and continue with more about the wave function in the next video, because it's gonna be a long video if I keep talking. So I'm gonna stop here.